And now, please let me introduce Vinnie Gautam. And she'll be talking about the breaking the wall of brain damage. Vinnie.
Thank you. Our brain is one of the most complex and perhaps one of the most important organs in the human body. And that's because it controls almost everything that we do in our daily lives, be it how we see, how we move, how we learn, or how we memorize stuff. Now, the brain does this with the help of millions of cells called neurons, which are connected with each other in a particular order, as you can see in the figure on your left. These neurons, which are connected in a particular order, form what we call neural networks. These neural networks form the basis of the functioning of the brain. When the brain gets damaged due to an injury or a disease, it is these neural networks which get disrupted and damaged. Now, the neurons, unlike other cells in the body, need to not just grow back, but also make specific connections in the neural network to regain their function after the damage. Currently, there are no drugs or treatments available to guide the neurons to form these connections with each other back as they were originally. Therefore, people are left with all sorts of disabilities, such as loss of vision, loss of movement, or even loss of memories of their loved ones. In my research, I am addressing this issue using principles in engineering and technology. What I'm creating are three-dimensional scaffolds which mimic the physical properties of the brain itself at the nanoscale, which is as small as 1,000 times smaller than the thickness of a human hair. These scaffolds, which mimic the physical and chemical properties of the brain, when implanted into the brain, would patch the area of brain damage by helping the neurons guide and form the connections into the neural networks back into their original form. Now, I have already started making these scaffolds, and I have preliminary results to show you that this idea can indeed work. In this image, you can see a single neuron sitting on top of my scaffolds, and the connections coming out of this neuron are guided by the nanoscale features of my scaffold. You can see the connections coming out of this neuron coming out in straight lines, which means that I can use the pattern of the nanostructures on my scaffold to guide the connections coming out of a single neuron. Now, not just a single neuron, what happens when we zoom out to a big group of neurons in a neural network? So here you can see that it's not just a single neuron, but my scaffolds with nanoscale features are able to guide the connections between multiple neurons within a neural network. So with my research, I aim to engineer neural circuits down to the nanoscale to break the wall of brain repair and brain damage. Thank you.
Thank you, Vinnie. And we have one question over here, Judith, and the second one.
What happens, if all of this works, what happens to your scaffold afterwards? Does it dissolve or does it stay in the brain?
Thank you. At the moment, my scaffolds are made of a different material, but we are trying to optimize the material so that these scaffolds are made of biodegradable materials. Once they have guided the neurons to form the neural networks, they would just dissolve in the body.
Sorry. Sorry, I've got the dreaded lurgy at the moment. The neural damage happens, and you really want to get something a repair mechanism to the cells very quickly, is my understanding. So, how feasible is that with a structure like this, and how would you deliver it to the brain damaged area?
Thanks for that. My idea is to design scaffolds based on the nanoscale geometry and the biophysical and biochemical properties that I'm optimizing on my on my scaffold. Ultimately, we would create an implant which would be implanted pretty quickly, as you mentioned, to the injury site, and then it would immediately act as a guidance cues. So the nanoscale features on my scaffold provide the guidance cues to the neurons on a very early stage, almost instantly.
And a question from my left.
How much control do you have over the network that is created? Can you control which connections you make with the neuron? So if you're looking at memory regeneration, probably you would want to restore some previous connection that was there before.
Yeah, great question. As at the moment, we are playing around with the specific geometry and the spacing and the diameters of these nanoscale features, which are mimicking the physical properties of the brain. So once we have the optimum conditions, we can regenerate the connections in the specific areas of the brain. So they would have to have different geometry for a different region. For instance, a different region which controls the movement would have different geometry of the scaffolds required, while the area of the brain which controls memory would need to have a different biophysical properties. So we need to play around with the structures of the scaffold accordingly, and we would design implants corresponding to that area of the brain which is damaged. Thanks.
I think I stop the discussion here in preference of time. So
Thank you.
Thank you very much, Winnie.